Hello everybody, my name is Mallory. I will introduce amorphous silicon TFTs to you. The A in amorphous silicon stands for amorphous. The H in front of the amorphous silicon tells us that the amorphous silicon is hydrogenated. Now the question is, why is the hydrogenation required? As you will see in the following slides, the disordered nature of amorphous silicon causes some atoms to have a dangling bond. These dangling bonds present defects which may cause anomalous electrical behavior. It is therefore desirable to have amorphous silicon passivated by hydrogen, which bonds to the dangling bonds, reducing their density. Typically, the hydrogen content in hydrogenated amorphous silicon is between 10 to 30 in atomic percent. About 95% of TFT LCDs use hydrogenated amorphous silicon TFTs. So how do we make amorphous silicon TFTs? Hydrogenated amorphous silicon is deposited by plasma enhanced chemical vapor deposition, which is abbreviated PECVD. The gas used for the PECVD is mostly silane, but disilane can also be used. The substrate temperature during the deposition is usually around 300 degrees C. Now, SiH3 radicals dominate the amorphous silicon film growth from the silane plasma. The schematic at the top left corner depicts the concept of the surface reaction process of SiH3 radicals reaching the film growing surface. The picture at the bottom here is an example of a PECVD equipment used for TFT LCD. This example is from Applied Materials and it consists of a multi-chamber cluster deposition system as schematized by the diagram at the top right corner here. The advantage of this system is that it allows the consecutive deposition of more than one TFT layer without breaking vacuum, leading to very clean interfaces. So what exactly does it mean to say the silicon is amorphous? Silicon is a four-fold coordinated atom that is normally tetrahedrally bonded to four neighboring silicon atoms, as you can see here in the top left corner. In amorphous silicon, the tetrahedral structure continues. In crystalline silicon, the tetrahedral structure continues over a large range, as you can see here, thus forming a well-ordered structure. However, in amorphous silicon, this long-range order is not present. The atoms form continuous random networks. And as you can see in the structure of amorphous silicon here, there are many dangling bonds. And as you learned from the previous slide, these dangling bonds can be compensated by passivating the amorphous silicon film with hydrogen. Now, at the bottom left corner here, we have the structure of amorphous silicon. The big red dots indicate the silicon atoms, and the small open circles represent the dangling bonds. Now, there are many flavors of amorphous silicon. namely nano, micro, and polycrystalline silicon. Here, there is some degree of order in the arrangement of atoms, but the order is in short ranges called grains. So here you can see that this part of the structure includes well ordered atoms. So this is a grain, and the space between two grains is called a grain boundary, and this is indicated by the question mark. So what is it that makes amorphous silicon TFTs so desirable for TFT LCDs? What are the limitations of this technology? Among the advantages of amorphous silicon, the TFTs can be fabricated using a low temperature process on glass substrate. Large area deposition is possible up to Gen 10 glass. The process is low cost compared to crystalline silicon, and among the limitations, the device performance of amorphous silicon TFTs is in the medium range, and this constitutes low field defect mobility, low leakage currents, high parasitic capacitance, and high photo currents. The first amorphous silicon TFT was reported by Lecombe in 1979. On the left, we have the transfer characteristics, where the drain current is measured as a function of the gate voltage. And on the right, we have the output characteristics, where the drain current is measured as a function of drain voltage. In 1981, Lecombe also reported the first application of amorphous silicon TFTs to active matrix liquid crystal displays. Here, amorphous silicon TFTs were used as pixel switching elements. TFT LCDs today use amorphous silicon for the same reason. So, what have we learned so far? We have learned what amorphous silicon is. We also learned that amorphous silicon TFTs are used as pixel switching elements in TFT LCDs. Now we are going to learn how to make amorphous silicon TFTs. There are many structures for amorphous silicon TFTs. By considering the location of the gate metal with respect to the location of the source and drain metal, amorphous silicon TFTs can either be staggered or coplanar. Now, if the gate is located at the bottom, the structure is referred to as inverted. So we have staggered and inverted staggered. We also have coplanar and inverted coplanar. Now, what do we use to classify these TFTs? It is simply the position of the gate metal with respect to the source and drain metals. Now, if we look at the TFT from the top, we can define the size of the TFT channel. And we have two distinct dimensions that people always refer to when they talk about the size of the TFT. We have the channel width, which is represented by W, and we also have the channel length, which is denoted by L. Now, how do we measure the channel length? The channel length is simply the distance between the source and drain electrodes, and the channel width is the width of the source drain metal in the direction orthogonal to the channel length. So how does a TFT function? Electrons are injected from the source and they are transported through the active layer all the way to the drain metal. Now, the channel conductance can be varied by varying the voltage applied to the gate. So the TFT becomes a 3-terminal device where the conduction from the source to the drain can be controlled by the voltage applied to the gate. So this channel area acts as a variable resistor with respect to the applied gate voltage. And if the TFT is symmetric, either this side or this side can be the source or drain. It doesn't matter which one is the source and drain. The two can be interchanged. Now, in order to fabricate a TFT, a mask which looks like a stencil is used to define all the shapes and sizes during layer deposition. For each layer, one design mask is used. So in this case, we have 1, 2, 3, and 4. I mean, you cannot see it here, but we have another one which is used to open the connection that connects the pixel electrode to the drain metal. So we have 1, 2, and 3 plus one last one, 4 different layers that need a different stencil. So for the amorphous silicon process, we require at least 4 design masks. As previously mentioned, the back channel edge structure is the most popular amorphous silicon TFT structure. Now we are going to learn how to make the metal electrodes, which is the gate and the source and drain electrodes, and how to make the gate insulator, which in this case is silicon nitride, and how to make the active region, which in this case is amorphous silicon. As usual, we start with the glass substrate. This is our glass here. Our glass. Now, one of the glasses of interest for display applications is a boroaluminosilicate glass. Now, a metal layer is deposited on glass by sputtering and patterned to form the gate electrode as indicated in A here. So we deposit a metal and then we pattern it using photolithography to form a gate metal. And how do we define this shape? We use a design mask, the gate mask, to design the shape and size of the gate electrode. After we make our gate electrode, we deposit silicon nitride, which acts as the gate dielectric. We also deposit the active region, which is intrinsic amorphous silicon, intrinsic hydrogenated amorphous silicon. And we also deposit an ohmic layer, which is N plus hydrogenated amorphous silicon. And after depositing these three layers, we define the active island. We pattern using photolithography and the active mask to define the shape of the active island as shown in B here. Another metal layer is deposited on top of the N plus amorphous silicon and patterned to form the source and drain electrode as shown in C. This is followed by the etching of the N plus region or the ohmic layer from the region that is between the source and drain electrodes. Now we want this region to be intrinsic so that we can easily control the conductance using the gate. If an N plus amorphous silicon layer remains here, then we lose the gate control of the channel region. Now, in order to protect the TFT from outside elements like the humidity or air, another dielectric layer is deposited on top of the device as the passivation layer. And finally, we form a contact wall, which is used to contact the drain electrode to the pixel electrode. Here is a list of the metals that can be used as electrodes. Now, moly is commonly used, but other alloys and other metals can also be used to lower the resistance, the contact resistance, or to improve the adhesion between the amorphous silicon and the metal layer. And similarly for the gate, moly and moly alloys are also used as gate electrodes. Silicon nitride is preferred for the gate insulator because of its high electric field breakdown, which is over 7 megavolts per centimeter, because of its low leakage current and absence of pinholes, and because of its high dielectric constant, which is between 6 and 7. The deposition of the passivation layer must be done at low power to avoid damaging the amorphous silicon. Now, let's move on to the current voltage characteristics of amorphous silicon TFTs. Now, for simplicity, the current voltage characteristics of MOSFETs can be applied to TFTs in their characterization. Similar to MOSFETs, the central part of the TFT, this part, corresponds to a MOS cap. We have here our metal, we have here our oxide, and we have here our semiconductor, making a MOS diode. When there is no applied voltage, the source and drain electrodes correspond to two PN junctions connected back to back. The only current that can flow from the source to drain is the reverse leakage current. Now, when sufficient positive bias is applied to the gate, the MOS structure is accumulated, because in this case our semiconductor is N-type. So when we apply a gate voltage, the MOS structure is accumulated, so that a surface of accumulation layer is formed between the source and drain, and as a result we have conduction from source to drain. In the extraction of amorphous silicon TFT parameters, the MOSFET current equation can be applied. Here, at low drain voltage, when the drain voltage is less than 1 volt, the TFT is said to be in the linear region. When the gate voltage is high, or when the gate voltage is equal to VG minus VTH, the device is said to be operating in saturation region. Now here, the CSINX is the oxide capacitance per unit area, μN is the field effect mobility, VTH is the threshold voltage, or in other words, the gate voltage at which the TFT turns on. W is the channel width, L is the channel length, VG gate voltage, VD drain voltage. The gate voltage swing is the inverse of the slope of log IDS as a function of VGS. This slide shows typical transfer and output characteristics of amorphous silicon TFTs. The field effect mobility is around 1 centimeter squared per volt second. The threshold voltage is around 3.7 volts, and the gate voltage swing is around 861 millivolts per decade. These are results for a device with geometry W over L of 100 micrometers by 4 micrometers. And as you can see in the left hand side figure, when we measure the transfer characteristics, we sweep VG and we hold the drain voltage at a specific voltage. So this is the transfer characteristics at a drain voltage of 1 volt. This one is the transfer characteristics at a gate voltage of 1 volt. This one at drain voltage of 5 volts, and this one at drain voltage of 10 volts. Whereas for output characteristics, we sweep the drain voltage and we hold the gate voltage at a specific voltage. Now this slide shows you how to extract these TFT parameters. Now the swing, which is simply the inverse of the slope of log drain current as a function of VGS, can be extracted from this line. So you get the slope of this red dotted line, and then you take the inverse. 1 over slope gives you the swing. So S here is equal to 1 over slope. Now this dashed blue line is the field effect mobility, which is calculated from the transconductance GM, and GM is given by the slope of ID versus VG at constant drain voltage, and this is equivalent to W over L CI. In this case, CI is the gate insulator capacitance, in this case the capacitance of silicon nitride, and mu is the field effect mobility, and V is the drain voltage. In this case we use a drain voltage of 0.1 volts. Now if you rearrange and make mu the subject of the formula, you will find that the mobility is given by GM times L divided by CI, VD, and W. So you do this and you get your graph here. So we take GM for small intervals so that we end up with a straight line. Not a straight line, but a function, a mobility as a function of gate voltage. Now the saturation mobility, you can see here we have the field effect mobility, which is obtained from this graph, and we also have the saturation mobility. Now how do we get the saturation mobility? The saturation mobility is extracted from the slope of the plot of square root drain current as a function of gate voltage. Now this drain current is different from this drain current. Why? Because this drain current is measured at VDS equal to 0.1 volts, whereas this drain current is measured with VDS equal to VGS. Now why do we do this? We do this to ensure that the TFT is operating in the saturation region. Now you have to recall that for the TFT to be in the saturation region, VD should be equal to VG minus VTH. That's why we have to measure these drain currents with VDS, or the drain electrode tied to the gate electrode. Now the mobility is derived from the slope of this curve, and from this curve we can also get the threshold voltage, which is simply the linear extrapolation of the curve. So this value here is our threshold voltage. In this case it was 3.7, as you can see here. Thank you.